Yeah, so my apologies. The internet was off, and as you probably noticed, the last video freezes towards the end for about a minute and a half. Yeah, so what I was saying is that by using kind of like this regression framework here, we have already shown that DI is relevant for the treatment. Yeah, so kind of can be regarded as an instrument. And if we kind of now want to estimate the treatment effect in a fuzzy regression discontinuity design, what we're doing is that, as in the sharp design, in the numerator, we are kind of calculating the effect of crossing the cutoff on the outcome variable. Yeah, so kind of what we see here is we see the jump, right? So we are just above the cutoff, and we look at the average outcome versus the average outcome just below the cutoff. That's simply the jump in the outcome while we cross the cutoff value. Yeah, so really, the jump due to the treatment. Yeah? And because we have a fuzzy design and only compliers actually change their behavior, so that's kind of only a subpopulation, we have to scale this effect by the fraction of the population that is actually changing their behavior. Yeah? So that is what we see in the denominator. Here we see kind of what is the change in the probability of receiving treatment just above the cutoff versus just below the cutoff. So kind of always remember that because TI is binary, writing the probability of TI being 1 conditional on X is the same as looking at the conditional expectation of TI given X. Yeah, so here we see that we scale the jump in the outcome by the probability change, yeah, by the jump in the probability when crossing the cutoff. Yeah, so, and because in the denominator, we are only considering the population that actually changes the behavior, so the compliers, and we can pretty much write this as this here. Yeah, so kind of the effect that we are estimating is well, the treatment effect for those individuals that are compliers, meaning they're kind of change their behavior, and we are still at the cutoff. Yeah, so kind of course, since we are having any RDD is kind of estimating something local, yeah, because well, we only have one cutoff, and therefore things have to be interpreted locally. However, kind of in a very famous paper by Lee in 2008, the author points out that in particular, this condition here does not necessarily mean that we only look at the subpopulation that has this X value exactly, because it may be that this subpopulation basically has, there's probability 0. For instance, if X is a continuously distributed variable, the probability that it takes the cutoff value exactly is actually 0, and therefore we will find no members of that subpopulation. Now, what that means, if we kind of write this here, it means that we're averaging, yeah, so the average treatment effect is a weighted average, and the weights are such that the individuals that are close to C, yeah, so that have a high chance of having X equal to C, those get more weight, and those individuals that have a high chance to be far away from the cutoff in terms of their rating variable, those get very little weight. So kind of if we're again thinking of a score, if a test score, so those individuals that, for instance, score extremely high, are very likely to score extremely high. Those get a small weight because they are far away from this cutoff with high probability. And those people that kind of are likely to score close to the cutoff, those get a large weight in the calculation of the treatment effect. Okay. Now, there is a couple of implicit assumptions that we need in order to interpret this effect as a causal effect. Yeah? So kind of what we need to assume is that crossing the cutoff does not simultaneously cause some individuals to take up treatment, whereas other individuals reject treatment. So that's kind of called monotonicity. And this assumption is introduced in the famous paper by Josh Angrist and Imbens, so about the local average treatment effect, econometrica. I don't know exactly what year, but this is an extremely influential paper. And of course, like in any regression discontinuity design, we have to make sure that while we cross the cutoff, X affects Y only through its impact on treatment reception. So kind of X can have a direct effect on Y, besides kind of this treatment, but that has everything else has to be continuous. So kind of like when X crosses the cutoff, it's really kind of the treatment that changes discontinuously. Everything else needs to change smoothly. Okay, so monotonicity, I think we have discussed before. If we haven't, here is kind of a reminder, or like a short explanation. So monotonicity is also an implicit assumption when we interpret instrumental variables. So kind of implicitly, we assume that the instrument does not lead to some people take up treatment, whereas other people reject it. So for instance, the famous example of Angrist Vietnam lottery. So remember that kind of for each day in the year, we had a lottery, so each day got a number. And if you were below a certain number, your birthday is below a certain number, then you were eligible for military service. And here, people that kind of would like to volunteer actually for the military, they would not be denied military service just because they have a too high lottery number. So monotonicity here in this example is, for instance, plausible. Okay, and as I said before, excludability really underlines that we need smooth changes. So kind of the treatment is the only thing that changes discontinuously at the cutoff. Everything else has to change smoothly. If there's anything else that also jumps at the cutoff, then of course we cannot differentiate between the jump due to the cutoff, due to the treatment, and due to this other variable. And this other variable would then be a confounding variable and mess up our causal interpretation. Okay, now we want to check the internal validity. Again, what is internal validity? Well, I mean, if you have a sample, it simply means that within that sample, your regression discontinuity design satisfies all the assumptions that are required for causal interpretation. So within your sample, you can draw a causal inference. Yeah. Okay. Now, whether or not you can extend from your sample or generalize from your sample to the total population, that's not a question of internal validity. That's actually a question of external validity. Yeah? So internal validity means within your sample, can you draw causal conclusions? External validity means, can you take these conclusions outside of your sample, generalize them to a larger population of interest? Yeah. Okay. Of course, well, like we now look at basically graphs that people use in order to check the plausibility of the internal validity, of the plausibility of the assumptions that are necessary for the causal interpretation. As of course, we need that there is a discontinuity in the probability of receiving treatment at the cutoff. Yeah? So we need to see a jump at the cutoff in the probability of receiving treatment. If there's no difference, no jump, forget it. There's no chance to do anything with the regression discontinuity design. Yeah? So that's easy to see because like look at the formula. If there's no jump in the probability of receiving treatment, we're basically dividing by 0. So that will not give us anything sensible. And of course, like also the rating variable and the cutoff point are like independent. So what is of course not good for your causal interpretation is that someone sets the cutoff in such a way that certain individuals get into the treatment group. Yeah? So that would be a violation of this independence assumption between the rating variable and the cutoff. And so for instance, if I have like as a teacher favorite students, but I know they're actually not the smartest, maybe I kind of choose the cutoff for the test score a little bit lower such that these people make it into the treatment. And then we have a confounding variable. Yeah? So kind of being a teacher's pet is then a confounding variable, for instance. Okay, now let's look at some plots. Yeah, so kind of we want to plot the relationship between non-outcome variables and the rating variable. Now, why is that important? In the lecture, we have stressed many times that only the treatment probability jumps discontinuously at the cutoff. If there's any other variable that also jumps at the cutoff, that means this variable will be a confounding variable. We cannot differentiate between the effect of the jump in treatment and the jump in this other variable on the outcome variable. So therefore, we don't have causality anymore. So if we have a non-outcome variable, something that should in principle be completely unaffected by the treatment. And we nevertheless, we see a jump of that variable around the cutoff, then that should ring all the alarm bells. Then the RDD is questionable for sure. So in our running example, remember that we had like a treatment for schools where a certain percentage of students lives under the poverty line. Let's say this cutoff presents a certain percentage of students in poverty. Also kind of at this cutoff, also the age structure changes discontinuously. So kind of it happens to be the case that at this cutoff, like, the schools that are just above and the schools that are just below, they differ in average age, for instance. Then age becomes a confounding variable, and treatment and control are different in more than one way. They are not only different in terms of the treatment, but also in terms of age, and therefore we cannot draw causal conclusions anymore. Okay. So here we have an example that what it could look like. So the non-outcome is age. The rating variable is the student's test score, I think. What was it? And here we see that at the cutoff, there doesn't seem to be any jump. So kind of here it looks like this is plausible, right? So here we don't find any evidence against the RDD design. Notice also that typically we cannot control for any non-outcome variable, right? There may be other variables that you don't have, so you cannot, it's just simply impossible to draw such a plot for any potential variables versus kind of the outcome variable. Therefore, you should do this kind of plot with whatever non-outcome variable you have in your data set. But of course, there can be, it doesn't allow you to prove the validity of the RDD design, right? It just makes it more plausible because you don't find evidence against the RDD design. That's something very different than finding evidence in favor of the RDD design, right? So here, these plots, they're only there in order to find evidence against the regression discontinuity design. We cannot prove that it's valid using these plots. We can just make it more plausible. Another thing is that we want to rule out manipulations of the rating variable. So for instance, so that we can do by checking basically the density of the rating variable. So we kind of want to see how many observations are to the left and how many observations are to the right of the cutoff. So if there's a clustering just above the cutoff, for instance, so that can be a sign of manipulation of the rating variable. So that can be a sign for either, for instance, the teacher sets, that's the example here, right? The teacher manipulates the cutoff value such that the students that the teacher thinks are nice, are worthy, they get the scholarship. So that would create a confounding variable. Again, as I said before, the students that are nice to teachers, being nice to the teacher, that's a confounding variable. In other circumstances, it can simply be that people can basically self-select into the treatment. So people have basically, they know more or less what the cutoff will be, and they have the possibility to jump just across the cutoff. So for instance, they basically have the possibility to self-select into treatment. And as usual, individuals self-selecting into treatment, that's never good for our causal interpretation. What we should see in that particular case is, as it says here, a jump in the number of observations just above the cutoff. So that's kind of the density plot that we see here. We see kind of here, there's very few observations kind of far away from the cutoff. Then we have quite some around the cutoff. And then all of a sudden, there's this huge jump. And we see here, it looks like the rating variable has been manipulated in such a way that people can self-select into treatment, or they have been selected into treatment and selected by a mechanism that is not just random. Yeah? So if it was really as good as random, we should see a nice smooth curve here. Yeah? And what we see is nevertheless this jump. That rings all our alarm bells, well, because it clearly violates one of the necessary assumptions of the regression discontinuity design. Yeah? And if you have a plot like that, yeah, that's bad for you. Yeah? You can basically throw your paper into the trash bin. Nobody's going to publish it. Yeah? Bad news. Okay, so far that's it about the regression discontinuity design. So far. Okay, bye bye.